may get extradited, and they caught the guy, and it was very successful. So there are some good use cases today of how we can adapt certain non-obvious signal information like that to build models on the adversary's mindset, which we can use for various purposes. So we touched on a few areas previously, but we're going to go into some more depth into those now. And there are various mechanisms that we can use today to perform analysis of attacks without automation, using a slightly modified version of what we as analysts do already. So we mentioned earlier exploit payload analysis, looking for known tool markings. Any of you that were in Greg's talk earlier, he spoke a lot about different tool markings and different compiler markings that you'll find within binaries. And actually Greg's tool that he's released will give you a list of the various markings that a compiler embeds into its code. Normally requires a manual effort to identify, but as Greg's shown, there are ways to automate that process. You'd be shocked at the amount of information that you'll find in binary images if you look hard, especially with lower end attacks. Everything from email addresses, references to MySpace pages, usernames and things like PDB debug strings, and so forth. So there's a lot of static information that often gets compiled into binaries as well that we can draw upon without having to develop too many more tools. Exploit analysis is something that I think in the incident response space we don't really do enough of. And the reason for that is exploits, there's a lot of work often that goes into an exploit when it's embedded within a piece of malware in order to modify it so it works better within that malware framework. So we're not talking copy and paste here from Millworm. There's a lot of effort that often goes into ensuring that that exploit is going to be successful based on the malware framework that it's now a part of. So improve reliability, specific targeting against different host operating system environments. And what a lot of this allows us to do is to create an automated framework, and actually this is something that I'm currently working on building into the tool that I'm going to release, is to compare exploit payloads with knowledge bases of, with a knowledge base of public exploits. So basically we can very quickly determine if a modification has been made to this exploit or not, which immediately tells us whether the malware was written by an adversary that has the ability to make modifications in that manner, and then perhaps flag that malware as something that we want to look at more closely to see exactly what those modifications were and tell us a lot more about the skill set of the adversary. A really good example of this is the ANI exploit a few years ago. This was a buffer overflow in Microsoft's animated cursor file format, and it was worked into a piece of malware. And what happened is 5 years before that, or maybe it was 4 years, there was another vulnerability in exactly the same file format, and everyone deployed IPS IDS signatures. And so what happened was, all of a sudden, there was this ANI exploit, very, very robust, but the 5-year-old IPS IDS signatures, it just so happened that they blocked the new attack as well. So what the malware authors did in this case is they were able to modify the exploit payload to get around these IPSs while still exploiting the vulnerability effectively. So that shows not only a significant level of skill that they were able to make those modifications successfully, but the fact that they did enough research to identify that their malware was going to get blocked by those IDS signatures ahead of time before releasing the malware. So reliability and performance is huge in the automated exploitation space. The quote I've got here, crashes and loose slips sink ships. The last thing you want happening if you've just spent a lot of money or spent a lot of time researching a new vulnerability that's not fixed by the vendor is for it causing crashes all over the internet, which are automatically getting reported to Microsoft so they can go and fix the bug. So reliability and performance is something that these guys look at very, very closely, and they'll focus on how they can improve the performance of the code. So improve shell code that may involve repatching of memory to ensure that the process remains stable post-exploitation. A good example of this is repairing of corrupted heaps. It's pretty common hat these days that after exploiting a heap condition, you'll call create heap to rewrite the heap area and allow the process to continue executing. But there are various technologies like that that we can observe that attackers may have modified their exploit to use to ensure that the system stays up. The program, whether it be a web browser or whether it be an RPC service, continues running and ultimately reaches the goal of the attacker that they now have the access to the system and no one's found out that they've been attacked, hopefully. Overhead is also a big consideration. A lot of the exploits for browsers that you'll see today, especially for those against ActiveX controls, a lot of those bugs basically involve referencing of uninitialized memory space. And what a lot of the attacks do is they'll create huge heap areas by using lots of JavaScript in a kind of a heap spray fashion. It'll allocate a lot of memory, and then eventually when you trigger what would have been an uninitialized memory reference, you'll hit your shellcode, hopefully. But the downside to that is, I don't know if you guys all use Firefox, but I do, and it already uses 200 megs of memory already. So, if this thing's using 2 gigs of memory because someone's done a huge heap spray, I'm going to be able to notice that. So, another thing that a lot of malware authors will do is they'll do a lot of research into the exploits to make them more reliable. So there's not going to be those other telltale signs of potential exploitation. And all of these, as we mentioned, mount to continued target process execution and the system remaining up. Another thing that we can often look at is also what is the nature of failure. Often a malware author will write a piece of code so that if they don't think they can compromise a certain system, they just won't attempt to break into that system. And that comes back to what we mentioned earlier, the perceived probability of success given attempt accessing a system. But in cases where the exploitation attempt has gone forward, is the exploit aware of any cleanup that might be necessary? Any of you that have caused crashes in Java will know that it dumps a nasty HS error log on the desktop, which is pretty much a red flag that someone's tried to own you. System application level log files are also very important on Windows, especially exploitation against Windows services. You'll find errors in the Microsoft application system and security logs that might be indicators of exploitation. And we don't see a lot of malware for Unix, but in that environment, core files are obviously very important to clean up. We mentioned being able to tune out attacks that are inappropriate earlier, and this again comes back to looking at the exploit and looking at what reconnaissance the exploit performed in terms of identifying the target operating system, language packs, and so forth. And ensuring that the exploit is applicable for that given operating system. So all of these things tell us a lot about the degree of forethought that the attacker placed into writing that malware to ensure that they would be successful. We mentioned ASLR and DEP. It's very difficult these days to get reliable exploitation against systems using hardware DEP and ASLR. With the exception of corner cases like application-specific exploitation, like against Flash using their just-in-time compiler technique. But a lot of malware these days will not attack certain platforms where there's a high probability that these anti-exploitation technologies may be in place. And again, if we're able to determine that a piece of malware does that, that tells us a lot about the forethought of the adversary in terms of not wanting to be caught. So these days there's also a lot of attention towards zero-day exploits, and a lot of folks really forget about the fact that old vulnerabilities are still very effective in many cases. A very novice reaction in the analysis world is to assume that anything except for a 0-day means that the adversaries are low-end or low-end in nature. Old attacks are often reworked to be very effective, to be a lot more reliable than the public exploit code that may have been released. There's a lot of cases where previous vulnerabilities may have been released and people may have thought that it wasn't really exploitable, but Microsoft may have fixed it already. So people may have deprioritized remediation of that issue, especially in big data center environments. Those kinds of considerations are always come into play. So it doesn't necessarily mean that they're a low-end adversary, and this is a great example of that. This is if my system will let me display the slide. Well, does anyone know what this is? There you go. So what this is this is a letter from a military employee in the Asia-Pacific Rim, and it's an email to a Booz Allen employee who is a project manager for a multi-role aircraft project. And basically what the email is it's an order for a multi-role aircraft, and it's very, very detailed. I mean, you have to do a lot of research to get all of the details that they had in this email. And attached to that was an exploit for a 2-year-old Microsoft Access vulnerability. Everyone knew about it. There were IDS signatures for it. And generally, it's, I run a pen test team, and it's not something I necessarily would have even tried. Yet, this adversary that spent so long finding out all of these details about what an order for a fighter jet looks like, decided that this is the exploit that they were going to use. So there's a lot more that you have to look at than just the exploit itself in terms of out-of-band information and preparation for an attack. And in this case, it demonstrates a lot of preparation on the part of the adversary in spite of the fact that they were using an exploit that at the time was 2 years old. Okay, so switching gears again, there are a number of other methodologies that we can use today which are commonly available to provide lineage between different exploits and code bases and malware and so forth. Isomorphism is something that's been studied in the security space, as far as I know, from around 2004, 2005. Isomorphism basically comes from the Greek shape and same, and what it's really saying is we're studying the same shape between different objects. And actually the word comes from the abstract algebra domain, but it's now used in security to really help us identify relationships between different code samples. And there are various ways that we can perform isomorphism, and these are just a handful of examples. This isn't an exhaustive list. Small prime product basically involves assigning a unique prime number to each opcode within a function. What you then do is add up the opcodes, and then that then gives you a sum of that function. And the neat thing about that is it's resistant to reordering of instructions. So if it gets compiled or someone's trying to be sneaky, it allows you to still have the same large prime number. And you may not necessarily want to assign a prime number to every opcode. You may just want to assign one to calls, to API calls, for example. API call structure analysis is another very common method which is used today. If you look at Halvar's tool, VX class, and BinDiff, I believe they use all of these methodologies to achieve lineage between different pieces of malware. There's an example here on the right of the screen where we have two programs, very basic example, but you've got two programs which are making a call to, I think that's regset key, reg key, query value, I can't see on my screen. Anyway, it's basically two registry API calls with a message box A in the middle of them in the first program. And in the second program, we've got the same functionality without the message box. And you would get a lot of false positives if you use this as a basis for analysis across a lot of programs because it's a very simple profile, but it demonstrates on a basic level how API call structure analysis functions. Function checksumming is very commonly used. MD5 is a common algorithm for this function, and also tracking of variables and constants across different programs where a variable has been defined in a specific function, or even better, a group of variables are being defined as static constants. We can use those variables to identify similar functions in different programs which use those same static variables, therefore increasing the chances that this code has been borrowed or is exactly the same code between different samples of malware. So some further reading if this is an area that interests you. There's a very good paper from, I'm not going to pretend to pronounce their names, but it'll be on the conference CD. And they produced a paper called The Static Birthmark of Executables. And these guys were looking at this for actually the purposes of piracy analysis. And what they wanted to do was to try and determine through API call structure analysis if we can tell if a piece of commercial software is potentially being